We'll start off the week by meeting another variant of the fruit class. And as you, I'm sure, recall from last week, the fruit class was putting in some pretty long hours, and I think it shows. It looks like it's slimmed down a bit since last week. So all this variant of the class does is it stores a single member called name, which is the name of a fruit, and it just prints out when the constructor is running and when the destructor is running. So it's not really the same thing we worked with last week. And the reason we're using this is because the alternative for an example like this would be something completely convoluted, like a class called A, something very conceptual. And I figure having something that's a bit more tangible is a little bit easier to talk about. And the reason we have to talk about that is because the main topic we're going to start with this week has to do with the lifespan of variables. We've spent all semester acting under the assumption that the lifespan of a variable is governed by its scope. We know by now that the class, the type of a particular variable, so class fruit for object of type fruit, the class gets control over how the object gets constructed and how it gets destroyed, and who can construct it. But it doesn't get control over exactly when it gets constructed. I mean, obviously you have to declare a variable of type fruit before a fruit exists. And we know that although the object gets control over what happens when it gets destroyed, the object does not get to control when it gets destroyed. That is a function, as far as we know, of the scope in which the object was declared. But just like in 111, we have reached a point in the course where we need to take control over the lifespan of objects that we create. So not the class, but us, the programmers creating the objects, might want to create objects with lifespans that are non-standard, that aren't matched up to the curly brackets of a scope. So we need to take manual control over the lifespan of objects. And you might recall in 111, this led us to the introduction of a feature that none of us were terribly fond of, the Malloc function. And we're about to meet a sort of C++ equivalent of that, which is a bit more structured, because unlike in C, when I create and destroy objects in C++, there's a lot more work that needs to be done. In C, creating an object with malloc amounts to just going and grabbing some memory somewhere. That's it. If you want to construct the object, you just have to do that yourself. Whereas we know in C++, if I create an object of type fruit, a constructor, if one exists, must be called. And similarly, when it gets destroyed, a destructor must be called. So what I want to talk about fundamentally is how do I create objects whose lifespan is some arbitrary thing, not governed by a scope. If I, the programmer, want an object whose lifespan is under my complete control. The most common reason we tend to do this is because I want to create an object, for example, inside a function, and I want that object to continue to exist when the function ends. I don't want to make a copy of it. I want the same object to continue to exist even when the scope in which it was created has ended. And that's the example I'm going to start with here. So I have this function called makeFruit. There it is, and we will notice that it's returning the altogether unsettling type fruit star. Recall from C that we read this as pointer to fruit. Now we are going to work with a few C-style pointers in the first few videos this week, and then we're going to stop. We're going to notice all of the reasons why C-style pointers cause us headaches and try and find an alternative. We've managed to work around C-style pointers so far in the course by using references, for example, and also by using higher level constructions. So to avoid having to work with, for example, C-style arrays, we've been working with vectors. We're actually going to see C-style arrays later this week as well, for the same reason, is that we're almost ready to be able to write our own vector class. We're actually going to do that this week. So I'm going to return something of type pointer to fruit. The reason why I have to work with a C-style pointer here is I need an actual pointer and not a reference for this. Because if I create any variable inside my makeFruit function, so if I create anything in here, it's going to get destroyed when the scope ends, period. Always. Any variable I create in the function gets destroyed when the function ends. So what I have to do if I want to create an object outside of the usual parameters of scope so that it doesn't get destroyed when the scope ends, I have to create my object sort of floating around in space. I can't create the object in the function because then it would be scope to the function. So I want to make an object that sort of floats around in the void outside of all functions. But then the question is, but how do I create the object inside a function then? Well, what I'll do, similar to what I do in C, is I will make a pointer that points outside of the scope of the function. And the type of the pointer will be fruit star. That is my goal. Now, the pointer variable, this thing, is going to get destroyed when the function ends. But this, the object that I'm going to create floating around in space, won't. And it'll be allocated manually. I will take complete control over its lifespan by allocating it manually. That of course, requires that I take responsibility for making sure it gets destroyed whenever I've decided that I'm no longer going to need it anymore. But we'll get to that part in a minute. For now, I want to figure out how to create such a thing. So I'm going to create a variable of type fruit star. I'm going to call it a fruit. And I'm going to now construct a brand new fruit object that exists outside of any scoped area of the program. So its lifespan is now indeterminate. And I'm going to use this operator called new fruit. And then I'm going to initialize it to be raspberry. I'm deliberately here using a C-style initialization, but you could do something like this. I've decided, having reflected upon it, that actually the C-style initialization might well look a little bit easier to work with, just because I know that pointers are nobody's favorite at this point, especially because it was a while ago since you've used them. So I'll use this just to get us back up to speed. But remember, as we've seen, especially with our discussions of things like copy construction, that C-style initialization is equivalent to uniform initialization. So we'll just take a pause on uniform initialization for this video while we warm back up to pointers. Okay, so here, this operation here, new fruit, is constructing a new object of type fruit, calling the constructor, they're the constructor arguments, and then returning to you a pointer to that object. The reason it has to give you a pointer is because the object doesn't really exist inside of the function. It exists somewhere else. And so you just get a pointer back to it. So I guess now I can polish off my diagram. So I've got this variable a fruit, and I've been given a pointer that points at this object, and we understand that fruit just contains a string, so we'll just write the word raspberry in there and conceptually understand that that's what the fruit object contains. Okay, so now I can return that pointer. All right, so I've written a function that dynamically constructs a fruit object containing the name raspberry and then returns a pointer to it. The object itself doesn't get destroyed when the function ends. The pointer gets destroyed, but we don't care about that. We don't really care about what happens when a local variable like a pointer or an int gets destroyed. The function returns a pointer to that object, and then the object lives on. The object lives on outside the function. As you recall from 111, there are lots of reasons you might want to do this. One of the big ones, one that we're going to need to come to soon, is constructing things like linked lists. In 111, when you want to make a linked list, you might want to write a function to add nodes to your list. The nodes you create in the function obviously need to outlive the function, and so you need some alternative to scoped allocation. All right, so that's the new operator. When I create an object with the new operator, I get a pointer to it, and then I can use the pointer as I see fit. But in using the new operator, I have told the language I will take responsibility for this object's lifespan. There is no need to automatically deallocate it. That's the point of the new operator. But it comes with that responsibility. I need to make sure that this object gets destroyed, because every object that gets constructed must be eventually destroyed. A destructor must eventually be called. And if it's my responsibility to ensure that, I better make sure it gets done. Okay, so we'll pause with the make fruit function for a minute and go down here and take a look at what we have in main. So in main, I create a fruit object with a new operator between main 1 and main 2. And we can see it's fruit star first fruit. And recall, unlike a reference, I am allowed, if I want to reassign a pointer later. So I could say first fruit equals new fruit, and then I could say grapefruit or something. Unlike a reference, where, as we know, I can set the reference to refer to something, and then after that, it functions as a second name for the same object. Recall from C that you're allowed to make a pointer point to anything you want at any time. I can reassign the pointer to point at something else. We're going to come back to that point later, because it turns out that causes one of the biggest headaches we have with memory allocation and pointers. And then down here between main 2 and main 3, I call the make fruit function. And that returns a pointer to a fruit containing the string raspberry. Okay, and so what I want to do here is demonstrate the converse of this. I use the new operator to make up a new object of type fruit, and in so doing, I take responsibility for its lifespan. What do I do when I've decided the object is no longer needed? How do I destroy it? It doesn't get destroyed automatically. And we'll talk about some implications of that fact in the next video as well. So the new operator has an inverse called delete. And the delete operator takes as its argument one of the pointers you were previously given by the new operator, and then it supervises the destruction and deallocation of the object. So when I use the delete operator, what I provided as the operand has to be something the new operator previously gave me. Additionally, I can't be trying to delete something twice. And maybe we'll try and experiment with that later, but formally it's undefined behavior. And so here I'll delete the object's second fruit. All right, and then we'll run the code. Oh, right. Okay, so I spelled it. For some reason, I wrote it backwards. There we go. Try that again. Okay, so I construct a pair. We can see that happening on line 38. This is the implication of line 41. So line 41 calls the make fruit function, and then make fruit returns the pointer to fruit. And then between main 3 and main 4, so on line 45, I destruct pair. I destroy the object that contains the string pair, and it gets deallocated. And then on line 50, I destroy the object containing the name raspberry. What I want you to observe here is first that I do seem to be upholding my end of the deal. So every object that I construct does get destructed. But also notice this doesn't follow the order that we're used to. We are not seeing the law of socks and shoes here. And the reason is because I have taken control. Normally, if I allocate this object first, it gets deallocated last. But here I've said explicitly, I want control. I want to decide when it gets deallocated. And I've shown that I have that control by deallocating them in an unconventional order. I've deallocated the pear first and the raspberry second. And so I think that's enough evidence that new and delete offer me something I didn't have already. The ability for an object to survive its scope. Notice that when the function returns, so that would be around here, I don't see a call to the fruit destructor. There's no copy being made. Instead, the same object is being returned from the function. So the function creates an object. The same object is what main ends up with. There is no copy being made. And the object lives on. The object continues living until just before main 5 here, so line 50. And then on lines 45 and 50, I manually deallocate with the delete operator the two things I've created. So this is a feature that we really should avoid using if at all possible. And by the end of the week, we will have found ourselves a way of never needing it again. We'll find a clever wrapper around new and delete that allows us to avoid having to use new and delete. In the meantime, we will see a few permutations of new and delete. One thing we should be aware of course, is if scoped allocation is good enough, we should always use it. In general, we shouldn't be taking on any responsibility that we don't need. And the responsibility to make sure that your object always gets deleted is a big one. And it's really easy to break that contract by accident. And that's what's called a memory leak, and we'll talk about that in the next video.